We're going to continue our discussion of 4.3. So the first part of 4.3 we looked at was the mean value theorem. Now I want to look at the first derivative test, which we explored in Lab 8. That's not how you spell it. First derivative test. All right. So from Lab 8, recall that we looked at, in Lab 8, we determined that if the derivative is positive for all x in some interval, open interval a to b, then f was increasing on that interval. All right, and then we said if f prime was negative for all x in our open interval a to b, then f was decreasing. So we explored this graphically, right? So if we have something like this, so on this side, where the function is increasing, then the slopes of our tangents are all going to be positive, and then on the other side, where it's decreasing, the slopes of our tangents, or the derivative, will be negative. All right? So when the function is increasing, then the derivative will be positive when the function is decreasing, or vice versa. All right? So that's one important result. In terms of the first derivative test, though, what we wanted to use this idea, right? Because here, on let's say the top of our thing is here, right? So there, at that point, we know that f prime, so let's call that c, f prime of c is 0. That's a critical point, all right? So let's say we have a critical point. One way to get a critical point is to find the point where the derivative is 0. We also know that critical points can constitute points where the derivative is undefined as well. But notice, so clearly this is a maximum, right? It's going up and coming back down the other side. Over here, f prime was positive, and on this side, f prime was negative. So we can summarize that result by saying that if f prime is positive, then f prime is negative on either side of a critical point. So what I mean by on either side is if it's positive to the left and then negative to the right, critical point, then f of c is a maximum of f. We should say local, right? Okay. Just means that if we go from one side or the other, the function values are going to be smaller. All right. So likewise, we can look at something like this. All right. So right here, we call that c. This is the point where the derivative is 0. Clearly on this side, the slopes of tangent lines are negative. The function is decreasing. And on the other side, slopes of tangent lines are positive. It's increasing. So again, if we go from decreasing to a horizontal tangent line and then increasing, we're going to have a minimum, right? So if f prime is negative and then it goes to positive, again, it's on either side of a critical point. Order is important, right? To the left, it's negative, and on the right, it's positive of a critical point. Then f of c is a minimum, local minimum of f. All right. Now, it's important to note that the derivative changes sign on either side of the critical point. Recall from lab, I don't remember what it was now, maybe lab 7, we looked at something like x cubed, right? That did something like this. This, we'll call it x cubed. All right, and right in here, I probably didn't draw it to where it flattens out enough, but we know that right at 0, 0, right, this thing flattens out, right? We can look at it also from the point of view, if we take the derivative, 3x squared, we set it equal to 0, that's going to be true when x is 0, right? So we're going to have a horizontal tangent line right at x equals 0. But what's the derivative over here? Those are all positive. The derivative is positive. And the same thing on the other side, right? F prime is positive. So there's no sign change on either side of this critical point. Therefore, there is no max or min. All right? Could be negative. We could have something that goes, for example, we'll just change colors here. If we come in something like this, you know, that could be negative x cubed, so its derivative is negative 3x squared. Set it equal to 0. It's going to have the same critical point, but over here, you know, you can see our tangent lines are negative, and on the other side they're negative, so we go from negative to negative. Once again, no max or min value at that point. All right, so that is just kind of summarizing what we were doing in the lab. Now I just want to go through a couple of examples of how to use the first derivative test. Okay, so let's take a look at this function. Bring this down a little bit. Okay, so with this function, 3x to the fourth minus 4x cubed minus 12x squared plus 5. All right, and so first we want to find the intervals of increase and decrease, and then we want to figure out what the critical points are and if they're max or min. All right, so the first thing we need is to find the derivative. This one's straightforward since it's a polynomial. We're going to end up with 12x cubed minus 12x squared minus 24x. All right, now a common factor there is 12x. That leaves us with x squared minus x minus 2. All right, and that can be factored. So we have 12x, that factors into x plus 1 and x minus 2. So let's set that equal to 0 to find our critical points. All right, so again, we have a product of three things here, and it equals 0. So that means either 12x equals 0, or x plus 1 equals 0, or x minus 2 equals 0. The only thing that would make that true is for x to be 0. If x equals negative 1, then that statement is true. And here, if x equals 2, that statement is true. So what I would like to do is just kind of go down here on a number line, and let's plot our critical points. So we have negative 1, 0, and then 2. Obviously not drawn the scale. And what we want to do is look at what are the intervals of increase and decrease. So what I need to do, I'm going to make a little sign chart for f prime. I want to find out, we know that f prime is 0, right? Here, here, and here. That's what we just did up here. We found the points where the derivative is 0, all right? And we found them to be these points. But now, in between, what's going on, all right? So if we pick something out here, let's say, now, I should say this. Notice, because the derivative is also a continuous function, that can only change signs by going through 0, right? That goes back to the intermediate value theorem. This thing can only go from positive to negative or negative to positive if it passes through 0. So I can pick any point out here. Everything out here, the sign of the derivative is going to be the same. It's going to all be positive, or all of them will be negative. And everything between negative 1 and 0, everything between 0 and 2, all of these intervals, the derivative is going to have the same sign for every value in the interval, because the only way it can change signs is for it to go through 0. All right? So we can pick anything we want out here. So let's try, I don't know, let's try negative 2. All right? And we want to put that back up here into our derivative and see what kind of, what's the sign. I don't even really care what the value is. I just want to know what the sign of the derivative when x equals negative 2. All right? So 12 times negative 2, and then negative 2 plus 1, and then negative 2 minus 2. All right. Well, that part clearly is going to be negative. Negative 2 plus 1 is going to be negative, and negative 2 minus 2 is going to be negative. Negative times negative times negative. This is going to give me, I don't know what the exact value is going to be. I could figure it out, but I'm too lazy, and I don't need to know it. I just need to know that this is negative right here. All right? So now let's pick something in between negative 1 and 0. For example, negative 1/2. All right? So now I've got 12 times negative 1/2, negative 1/2 plus 1, and negative 1/2 minus 2. So again, this right here, that's going to be negative. This will be positive, and this piece right here will be negative. Negative times a positive is negative times a negative. That's going to be positive right here. All right, now I want to pick another test value somewhere in between here. 1 seems like a good choice. So when x equals 1, I have 12 times 1, and then 1 plus 1, and then 1 minus 2. So this, positive, positive, negative. So if I multiply these all out, I get a negative. So that's negative. Finally, pick something greater than 2. Whoops, I picked x equals 1 here. And down here, I picked x equals, I don't know, let's try 3. 12 times 3 times 3 plus 1 plus, or times 3 minus 2. So that's positive, positive, positive. The product of 3 positives is a positive. Okay, so we know the function is increasing. So let's just write this down then. The function is increasing on the interval from negative infinity. Whoops, sorry, let me change that. Out here it's decreasing, right? So let's say it's decreasing from negative infinity up to, but not including 1, right? Right at 1, the derivative is 0, so it's neither increasing or decreasing at that point. And then I have this other interval in here where it's decreasing from, so I can union this with the interval from 0 to 2. And then increasing, right, I have this interval here from negative 1 to 0. Again, these are open intervals. It doesn't include the endpoints because we know the derivative at the endpoints is 0, so it's neither increasing nor decreasing. So I've got negative 1 to 0, and then I can add to that 2 to infinity. All right. Now I have these 3 critical points. I want to use the first derivative test to determine if each of those are a local max or a local min. Well, here we can kind of think about what's going on here. My function is decreasing, and then it's 0, and then it's increasing, right? Just kind of using those signs. So at x equals negative 1, I have a minimum, and then it's positive, it's 0, and then it's decreasing along here. So at x equals 0, I have a maximum. And then once again here, it's decreasing, it's 0, and it's increasing. So at x equals 2, I have a minimum. Okay, I want to do one more example. Oops. All right, last example here of how to use the first derivative test. I want to look at the function y equals x plus 1 over x. And I just want to use the first derivative test to, well, first, I want to find out where the local max and mins of this function are. So the first step is to find the critical points. All right. So I take the derivative. That gives me 1, and the derivative of 1 over x, we've already done that. That's negative 1 over x squared. And I set that equal to 0 to try to find the critical points. All right. So if I add negative or add 1 over x squared to both sides, I want to find the points where 1 equals 1 over x squared. All right. Before I get too far, hopefully some of you in the back of your mind are saying, but Dr. Sherman, isn't it don't I also find critical points where it's undefined? Absolutely. We'll come back to that. It's kind of obvious if you look at this where the derivative is undefined. But let's look at this first, all right? In order for this to be true, I need x squared to equal 1. That's going to happen when x equals plus or minus 1. And clearly, just looking at this right here, we can tell that the derivative will be undefined. So this is where the derivative equals 0 at these points, and then this is undefined when x equals 0. So I'm going to make my little number line again down here again. I'm going to put my critical points on it. So I've got a critical point at -1, at 0, and at 1. All right. So again, I'm making a sign, basically like a sign graph for f prime. I know that f prime is 0 here, here, and here. I'm interested in what the sign of the derivative. Whoops, for f prime. I'm interested in the sign of the derivative in between, because that will tell me whether or not I have a max or a min, or neither at these critical points. All right. So let's again pick some test values. So I can pick anything less than -1, because I know the signs don't change on these intervals. So let's pick, I don't know, -2. So at x equals -2, if I put that into this expression, I get 1 minus 1/4, right? Because if I square 2, I get 4. That's positive. All right, so out here, the sign is positive. Now let's pick something in between -1 and 0. So let's pick like, I don't know, -1/2. And if I do that, if I put in -1/2 here, I square to get positive 1/4. And 1 divided by 1/4 is 4. So that's 1 minus 4. Obviously, that's negative. So negative here. Let's pick something in here. Let's do positive 1/2. That will also be, because I'm squaring, I'm going to actually get the exact same thing for negative and positive 1/2. 1 minus 4, that's negative. And then coming out here on this side, you know, if I pick positive 2, then I get the same thing as I got up here, right? Because when I square it, I end up with positive. So 1 minus 1/4, that's positive. So this is positive. All right. So now we look here. We know that our function. We don't know. Well, of course we can graph it, but just using this, we know that our function is. Wrong way. Our function is increasing. Let me fix that. Our function is increasing, and then it's 0, and then it's decreasing. So at x equals -1, clearly, we have a maximum. Now here, my function is decreasing, then it's 0. Well, actually it's not 0, sorry. I screwed that up. Right here it's undefined. Well, let's just say does not exist. All right. It's a critical point, but it's not a point where the derivative is 0. It's a point where the function, or the derivative does not exist. So you could have something that looks like it could be decreasing, and then over here, it's maybe still decreasing. All right. Notice that let's go back to the original function. Notice that the function is not defined at 0 either. So because we can't put 0 in. I mean, it's 0 here, but that's undefined. So we have a problem there. The function, there is no function value associated with 0. So this thing is decreasing on either side of that critical point. So at x equals 0, we have neither. It's a critical point, but it's neither a max nor a min. And then over here, we're going from decreasing, 0, and increasing. So clearly that's a minimum. So at x equals 1, we have a minimum. So this is how we use the first derivative test to test our critical points. So just quick review, we found our critical points. We set it equal to 0 to get these. We look where it was undefined to find that. And then I make this sign diagram, and nice when I do it right the first time, but hopefully you guys follow what we're doing there. We just want to look at the signs in between these intervals. Here it was 0, here it did not exist, and we can use the sign change, if there is one, to determine if it's a max or a min, and then if there is no sign change, it's neither.